Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The sage of the Smithsonian Joseph Henry's Electromagnetism accounts of technological genesis often seek a singular progenitor, a solitary mind from which a world-altering invention springs forth fully formed. The telephone, an instrument that dissolved distance and rewove the fabric of human society, is almost universally associated with the name Alexander Graham Bell. This clean, linear narrative, while compelling, is a profound simplification. It omits the colossal intellectual foundations upon which Bell's specific genius was ultimately applied. To comprehend the emergence of the telephone, one must first turn away from the acoustic workshops of Boston and travel back decades to the laboratories of a man who commanded the subtle and formidable force of electromagnetism. We must begin with Joseph Henry, a physicist of the first rank and the quiet, undisputed sovereign of American science in the mid-19th century. His work provided the essential grammar for the electrical age. The scientific world, the widely 800 times, was captivated by a new and mysterious phenomenon. Hans Christian Oersted's 1008th discovery that an electric current could deflect a magnetic compass needle had electrified the scientific community, with André Marie Ampère in France quickly providing a brilliant mathematical framework for the force. The English inventor William Sturgeon had demonstrated in 825 that wrapping a live wire around an iron core could create a temporary magnet. Yet these early electromagnets were feeble things, scientific toys capable of lifting a few ounces, their potential constrained by a fundamental engineering challenge. The insulated wire of the day was typically coated in varnish or wound with loosely spun cotton, preventing the coils from being packed tightly. Any attempt to increase power by adding more turns of wire resulted in a bulky, inefficient apparatus where currents would often short circuit, leading away their force. The problem was one of concentration and scale. The principle was known, its power remained latent, a whisper of a force awaiting its amplifier. Into this context stepped Joseph Henry, then a professor at the Albany Academy in New York. Possessing a mind that fused profound theoretical insight with a sublime practicality, Henry perceived that the path to power lay in insulation and configuration. He required a material that was thin, strong, and superior to electric. The solution, in a famous and perhaps apocryphal tale, came from his wife's wardrobe. Using strips of silk from her petticoats, he meticulously wrapped every inch of his copper wire. This fine, durable insulator allowed him to wind hundreds, even thousands of turns into a dense, compact coil around an iron core. Each wrap added its magnetic effect to the whole, creating a cumulative force previously unimaginable. With this superior coil, Henry developed a crucial conceptual distinction that guided all subsequent electromagnetic engineering. He designed two types of magnets for two distinct purposes, each matched to a specific type of battery. The first he called a quantity magnet. It featured numerous short, parallel coils of wire connected to a quantity battery, a single large electrochemical cell producing a low voltage but high current. This design was an engine of brute force, optimized for maximum lifting power at close range. His second, and arguably more consequential, creation was the intensity magnet. This device employed one continuous, extremely long coil of wire, sometimes over 1,000 feet in length. It was designed to be powered by an intensity battery, which consisted of many small cells wired in series to produce a high voltage. The practical demonstration of these principles was staggering. In 1831, working at Yale, Henry constructed a monumental electromagnet. Using his silk-insulated wire and refined mining technique, he created a device that lifted a payload of 2,063 pounds over a ton. The world record was shattered, and the electromagnet was transformed from a laboratory curiosity into a formidable industrial tool. This achievement was more than a display of raw power. It was a demonstration of a deep understanding of electrical circuits. Henry had articulated the relationship between the internal resistance of the battery and the external resistance of the coil, a concept that would later be formalized by Georg Ohm, whose work was still largely unknown in the United States. Henry's intensity magnet, with its high resistance coil matched to a high voltage source, was the key to overcoming the resistance of long transmission wires. It was a fundamental component required for sending a detectable electrical signal across a significant distance. Henry's explorations continued to uncover foundational principles. In 1832, he observed a curious effect. When disconnecting a long coil from a battery, a brilliant, sharp spark would leap across the switch contacts, far more intense than the spark produced by a short wire. He correctly deduced the coil's own magnetic field, upon collapsing, induced a secondary, momentary current back into the wire itself. He had discovered the principle of electromagnetic self-induction. This phenomenon, where a circuit resists changes in current flow, is a cornerstone of electrical engineering, the operating principle behind every inductor, choke, and transformer that regulates the flow of electricity in modern electronics. He published his findings in the American Journal of Science, securing his place as a discoverer of a fundamental physical law. The impact of Henry's work was direct and transformative, particularly on the development of the technology that would precede the telephone. In the 1830s, the artist and inventor Samuel Morse was wrestling with the concept of an electric telegraph. His vision was clear, but his understanding of the electrical principles involved was incomplete. He struggled to make his device work over more than a few feet of wire. In a pivotal meeting in 1837, Morse visited Henry, who was by then the esteemed first secretary of the newly established Smithsonian Institution. Morse explained his predicament. Henry, with the patience of a seasoned professor, explained the crucial distinction between his quantity and intensity magnets. He advised Morse that for a long-distance telegraph, it was essential to use an intensity magnet with a high-voltage battery composed of many cells in series. This configuration would create a signal strong enough to overcome the resistance of miles of wire and activate a receiver. Henry also suggested the use of an electromagnetic relay, one of his own inventions, to regenerate a weakened signal over even greater distances. He was, in effect, handing Morse the scientific keys to a workable intercity telegraph. Morse's genius was in his persistent vision and the creation of his elegant code, The physical means of its transmission across a continent depended entirely on the foundational science established by Joseph Henry. Before a single word could be spoken over a wire, a simpler signal had to be sent, and Henry's work made it possible, establishing him as the intellectual giant whose shoulders would support the next generation of electrical inventors. A scientific bedrock established by Joseph Henry provided fertile ground for a new generation of inventors, each seeking to cultivate the commercial potential of the electric current. Among them was a figure whose expertise came from a different world entirely, a world of acoustics, physiology, and the mechanics of human speech. Alexander Graham Bell arrived at the problem of electrical communication with a perspective shaped by his family's deep immersion in the science of elocution. His father, Alexander Melville Bell, was the creator of a system called visible speech, a universal phonetic alphabet that represented the position and movement of the throat, tongue, and lips in producing sounds. The younger Bell was therefore conditioned to think of communication as a physical, vibratory phenomenon, a series of complex waves to be analyzed and reproduced. His approach to the telegraph, the dominant electrical technology of the day, was consequently one of an acoustician, a specialist in sound confronting a problem of electricity. The challenge that captured his imagination was one of commercial urgency and technical elegance, the limitations of telegraphic bandwidth. By the mid 1870s, the telegraph had become the central nervous system of commerce and news, yet each wire could carry only one message at a time, a frustrating bottleneck that drove up costs and slowed communication. The great prize, pursued by inventors like Elisha Gray and Thomas Edison, was a multiple or multiplex telegraph, a device capable of sending several independent messages over a single line simultaneously. Bell's solution to this quintessentially electrical problem was born from his deep understanding of musical harmony and acoustic resonance. He envisioned what he called a harmonic telegraph. The concept was a marvel of cross-disciplinary thinking. It proposed a transmitter consisting of several steel reeds, each precisely tuned to a different musical pitch. When a telegrapher pressed a key, an electromagnet would cause the corresponding reed to vibrate at its unique frequency, sending a pulsating electrical current down the line. At the receiving end, a matching set of tuned reeds would be arrayed near another electromagnet. The incoming electrical signal, oscillating at a specific frequency, would induce a sympathetic vibration exclusively in the one receiver reed that shared its natural resonant frequency. All other reeds would remain silent. In theory, one could send messages on the frequency of C sharp, while another operator simultaneously sent a different message on the frequency of F, all traveling together as a composite wave down the same physical wire before being neatly sorted by their respective receivers. It was, in essence, the application of a symphony orchestra's principles to the telegrapher's key, a system today we would recognize as a direct ancestor of frequency division multiplexing. This intellectual synthesis was powerfully catalyzed by a fortuitous encounter with German science. While struggling to perfect his device, Bell acquired a copy of Hermann von Helmholtz's magisterial work, on the sensations of tone as a physiological basis for the theory of music. Bell's command of German was incomplete, and this limitation produced one of history's most fruitful misunderstandings. He studied a diagram depicting an apparatus Helmholtz used to analyze and synthesize complex vowel sounds. The device used electrically vibrated tuning forks to create the constituent frequencies of a vowel. Bell, through his linguistic filter, misinterpreted the diagram's purpose. He believed Helmholtz had devised a way to transmit vowel sounds themselves over a wire. The implication was staggering. If individual vowels could be sent, then with sufficient complexity, the continuous, flowing waveform of all human speech could be electrically transmitted. This beautiful error fused his work on the harmonic telegraph with a far grander, more profound ambition. Armed with this vision, Bell pressed on with his experiments, which he documented with meticulous care. His U.S. patent number 161, 18739, for improvements in transmitters and receivers for electric telegraphs, filed in March 1, 1875, provides a tangible record of his thinking. The document details the mechanics of his tuned reed system, laying out the entire architecture of the harmonic telegraph. His days were consumed in his Boston workshop, a space filled with the sounds of vibrating reeds, a hum of electromagnets, and the scent of shellac. He spent countless hours filing the steel reeds by hand, attempting to achieve perfect tuning, a task of immense delicacy and frustration. He worked alongside his talented assistant, Thomas Watson, wrestling with the practicalities of induction, resistance, and the finicky behavior of his electromagnetic apparatus. This period was also one of immense personal and financial pressure. His work was funded by two patrons, Gardner Hubbard, a prominent Boston lawyer, and Thomas Sanders, a wealthy leather merchant. Both men were fathers of deaf students whom Bell tutored, and they were investing in the promise of the harmonic telegraph, a practical device with clear commercial value. They saw a return on investment. Bell was increasingly haunted by the whisper of a speaking machine. This divergence in ambition created a palpable tension. Bell's patrons grew impatient for a marketable multiplex telegraph, while Bell's mind was increasingly captivated by the more speculative and perhaps less profitable idea of transmitting the human voice. His relative isolation from the core of the American scientific establishment compounded his difficulties. He was a brilliant and intuitive experimenter, yet he lacked the formal theoretical training in physics and electricity of his contemporaries. He struggled with concepts of impedance matching and electromagnetic induction that a university-trained physicist might have navigated with greater ease. His progress was a testament to his relentless tenacity and his unique acoustic insights, a process of empirical discovery through endless trial and error. He was building a bridge between two disciplines, sound and electricity, largely from his own intellectual materials. The harmonic telegraph worked perfectly, crossed arc between the channels and the difficulty of maintaining precise tuning plagued his demonstrations. He had conceived a brilliant answer to the multiplexing problem, yet he found himself mired in the technical challenges of its execution, all while a more revolutionary idea was demanding his attention. He stood at an intellectual crossroads, possessing the germ of two world-changing inventions, but feeling the full weight of his own scientific limitations. He needed guidance, validation, and a deeper understanding of the physical laws that govern his electrical dream. A mind wrestling with the stubborn physics of tuned reeds and intermittent currents carried Alexander Graham Bell to Washington, D.C. in the winter of 1875. He arrived with his harmonic telegraph apparatus, a device of profound ingenuity, yet one that stubbornly resisted perfection. The more audacious concept, the transmission of articulated speech itself, remained a theoretical ghost haunting his workshop. an idea whose grandeur was matched only by the inventor's own deep-seated anxiety about his command of electrical science. This feeling of intellectual isolation propelled him toward the one man in America who could resolve his doubts, Joseph Henry, the venerable secretary of the Smithsonian Institution and the nation's foremost physicist. The pilgrimage was one of an aspiring inventor to the established oracle of American science, a young man seeking from the elder statesman both technical clarification and, perhaps more importantly, authoritative sanction for a revolutionary dream. The meeting, which took place in March, began with a demonstration of the familiar. Bell, with the nervous energy of a doctoral candidate defending his thesis, laid out his multiplexing telegraph. He explained its operation, its reliance on sympathetic vibrations, and the economic problem it was designed to solve. Henry, a figure of immense intellectual gravity, listened with patient, focused attention. His own pioneering work decades earlier, which had established the principles of electromagnetic induction and the construction of powerful electromagnets, gave him an unparalleled vantage point from which to assess Bell's work. He recognized the cleverness of the acoustic analogy and commended Bell on the elegance of the solution. This initial praise, coming from such a source, was itself a significant affirmation for the young inventor. Emboldened, Bell hesitated, then took the greater intellectual risk. He confessed that another, more speculative idea occupied his thoughts. He began to sketch, with words and diagrams, the concept of a speaking telegraph. He articulated his central theoretical breakthrough, the necessity of an undulatory current. He explained that to transmit the complex waves of human speech, the electrical current must vary in intensity precisely as the air pressure varies when a sound is made. It was a concept of breathtaking elegance, a direct mapping of the acoustical world onto the electrical. He was proposing a continuous, analog signal, a stark departure from the binary on-off pulses of the existing telegraph. He was describing the very soul of the telephone. Here, the dialogue shifted from a demonstration of a working device to a consultation on a theoretical possibility. Bell's vulnerability became apparent as he posed a question that exposed the limits of his formal training. He wondered aloud if an induced current, however perfectly it might mimic a sound wave, could ever be strong enough to overcome the immense electrical resistance of a long telegraph wire. His thinking was still conditioned by the brute force logic of powerful batteries. Henry's response was immediate and transformative, drawing directly from the wellspring of his own foundational research from the 1830s. The critical factor, he explained, was the magnet. A more powerful electromagnet, properly designed, would induce a correspondingly stronger current. The solution lay in the architecture of the induction system itself, a domain where Henry was the undisputed master. He was, in effect, handing Bell the specific key he lacked, reorienting his experimental focus from galvanic cells to the subtleties of magnetic field design. This piece of technical counsel, while invaluable, was secondary to what followed. Sensing the full weight of the project on Bell's shoulders, Bell confessed his own perceived inadequacy. "I have not the electrical knowledge," he lamented, suggesting that he should publish his idea and allow a more experienced physicist to build the apparatus and claim the credit. It was a moment of profound self-doubt, and offered to surrender his own intellectual progeny. Henry's reply became one of the most consequential exhortations in the history of invention. He leaned forward and, with the full authority of his position and reputation, declared, "You are the germ of a great invention. Worked at it." Some accounts render his words even more directly dead it. The effect of this statement on Bell was electric, a shock of pure validation that resolved his internal crisis. He had arrived at the Smithsonian a talented but anxious inventor, caught between a viable project and a visionary obsession. He departed to man with a mission, armed with a clear directive from the highest scientific authority in the land. His correspondence and diary entries from the period radiate a new confidence. The psychic burden of his perceived ignorance was listed. Henry had given him permission to learn, to experiment, and to succeed on his own terms. The telephone was elevated from a speculative fancy to his primary, all-consuming quest. The harmonic telegraph, once the centerpiece of his ambition, now became a subsidiary project, a source of funding and a field for related experimentation. Henry's role in the saga of the telephone extended far beyond the single, catalytic encounter. As Bell's work progressed and eventually culminated in a functional device, Henry became its most powerful and credible champion. In the face of public skepticism and the ferocious legal challenges that would soon erupt over patent priority, Henry's endorsement was a shield of unimpeachable credibility. He provided a sworn affidavit in 1877, testifying to Bell's early disclosure of the core principle of undulatory currents. He later stood before committees and courts, a figure of immense scientific and moral stature, and affirmed the soundness of Bell's science and the priority of his invention. This public validation was a crucial social and legal counterpart to the private encouragement he had offered in his Smithsonian office. The Bell's 1875 meeting was the beginning of an intellectual sponsorship, where the elder statesmen of American physics recognized the future and, with a few well-chosen words of technical advice and personal encouragement, empowered a new generation to realize it. He passed a conceptual torch, ensuring that the fundamental principles of electromagnetism he had helped uncover would find their most remarkable application in the hands of the determined young man who had come to him for guidance. Armed with the sanction of America's preeminent physicist, Alexander Graham Bell returned from Washington to his Boston workshop with a renewed and singular focus. The conceptual ambiguity that had clouded his efforts had dissipated. Joseph Henry had affirmed the core idea, the germ of a great invention, and the path forward, while technically arduous, was intellectually clear. The challenge was immense: to create an apparatus capable of translating the delicate, continuous waveforms of human speech into a perfectly analogous electrical signal. This required a fundamental departure from the established world of telegraphy, which operated on a binary system of intermittent sequential pulses. Speech, with its infinite gradations of pitch and volume, demanded a current that could ebb and flow, a current that undulated. The workshop at 5 Exeter Place became the crucible of feverish experimentation. Here, the theoretical elegance of the undulatory current met the stubborn realities of metal, wire, and acid. Bell, with his deep knowledge of acoustics and phonetics, provided the vision. His gifted assistant, Thomas A. Watson, a skilled mechanic and electrician, provided the technical prowess to translate those ideas into tangible forms. Together, they explored countless configurations. They attempted to use vibrating reeds and tin forks, remnants of their work on the harmonic telegraph, but these devices were ill-suited for the complex, non-repeating patterns of speech. The problem lay in finding a mechanism that could vary the resistance within an electrical circuit smoothly and in direct proportion to the pressure of a sound wave. The solution arrived through a combination of meticulous work and serendipity. On March 10, 1876, Bell was preparing an experimental apparatus that would become known as the liquid transmitter. The device was conceptually brilliant in its simplicity. A small diaphragm, designed to vibrate when struck by sound waves, had a conductive needle attached to its center. The tip of this needle was immersed in a small cup of acidulated water, a conductive fluid. When Bell spoke into a mouthpiece aimed at the diaphragm, the vibrations caused the needle to move up and down in the acidic solution. As the needle submerged deeper, the path for the electrical current through the liquid shortened, decreasing the resistance. As it rose, the resistance increased. The result was an electrical current whose intensity mirrored, with remarkable fidelity, the acoustic waveform of his voice. This was a physical embodiment of the undulatory principle, the very concept Henry had encouraged him to pursue. The successful test that day is passed into legend. While adjusting the transmitter, Bell accidentally spilled some of the battery acid on his trousers and reflexively cried out, "Mr. Watson, come here, I want to see you." Watson, working in an adjacent room, with a receiver pressed to his ear, device consisting of an electromagnet and a thin ion diaphragm, heard the words clearly. It was the first time in human history that articulate speech had been transmitted and reproduced electrically. The sound was faint, the apparatus crude, yet the principle was proven beyond all doubt. The conceptual torch Henry had passed a year earlier had now ignited a technological revolution. This breakthrough, however, was preceded by an act of extraordinary foresight and urgency. Aware that other inventors, particularly the talented Elisha Grayach Cargill, were exploring similar territory, Bell's financial backers insisted he secure his intellectual property. On February 14, 1876, a day now famous in the annals of invention, Bell's attorney filed his application at the U.S. Patent Office in Washington, D.C. In a turn of events that would fuel decades of litigation, Elisha Gray filed a caveat, a formal declaration of an intention to file a patent for a similar liquid-based transmitter design on the very same day. Bell's application, which was granted on March 7, 1876, as U.S. Patent 174465, is widely regarded as the most valuable single patent ever issued. Its power lay in its breathtaking scope. While it described a specific apparatus, its most crucial component was its fourth claim. This claim articulated the method of and apparatus for transmitting vocal or other sounds telegraphically by causing electrical undulations, similar in form to the vibrations of the air accompanying the said vocal or other sound. This language was a masterstroke of legal and scientific synthesis. It protected the entire principle of transmitting speech, fire, and undulatory current. Bell had patented the fundamental concept, a far more powerful protection than a patent on any single piece of hardware. It secured the territory Henry's guidance had helped him map. In the contentious legal battles that followed, the full value of Henry's endorsement became manifest. The patent interference case with Gray and later challenges from other inventors hinged on the question of priority of conception. Who first understood the principle of the undulatory current as the key to transmitting speech. It was here that Joseph Henry, the elder statesman of science, stepped from the quiet of his laboratory into the public glare of the courtroom. He provided sworn affidavits and direct testimony affirming that Bell had explained the core principle to him in detail during their meeting in March of 1875. Well, before Gray's documented work, Henry's word was a shield of unimpeachable scientific authority. Before committees and judges, his presence lent immense weight to Bell's claims. He was a figure above the fray of commercial competition, a man whose life was dedicated to the pursuit of knowledge for the public good. His testimony that Bell possessed the germ of a great invention and understood its underlying science was devastating to the counterclaims of his rivals. The private encouragement offered in the Smithsonian office was thus transformed into a decisive public and legal weapon. It demonstrated a powerful symbiosis. Henry's foundational science and moral authority provided the conditions under which Bell's applied genius could be both realized and legally protected. This period, from the spring of 1875 to the spring of 1876, represents a perfect case study in the translation of scientific principle into world-changing technology. It was a process driven by Bell's relentless ingenuity and Watson's collaborative skill, but it was anchored and validated by Henry's wisdom. The invention of the telephone was the culmination of Bell's own tireless work, yet it stands as a profound testament to the power of mentorship and the critical role that established science plays in fostering radical innovation. The successful transmission of a few simple words from one room to another created more than an echo. It announced the birth of a new era of global communication and set the stage for a profound divergence in the legacies of the two men who, together, had made it possible that divergence crystallized around a fundamental question concerning the very purpose of discovery. With the telephone a tangible reality, the paths of Joseph Henry and Alexander Graham Bell separated, each man coming to embody a distinct, powerful, and enduring philosophy of innovation. Their subsequent careers offer two archetypes that continue to shape the landscape of science and technology. One path led to the quiet, foundational work of building a national scientific institution. The other led to the creation of a global commercial empire. The intellectual problem their legacies pose is profound. How does a society best cultivate progress? Is it through the open dissemination of foundational knowledge or through the protected, incentivized development of specific applications? The lives of Henry and Bell, after one, 1876, provide a compelling, real-world exploration of this essential tension. Henry's vision was one of magnificent public-mindedness, a philosophy he had championed his entire life and which found its ultimate expression in his stewardship of the Smithsonian Institution. Appointed its first secretary in 1846, he established the institution's mission based on a literal interpretation of James Smithson's request for the increase and diffusion of knowledge among men. For Henry, this meant that the institution's resources were to be directed toward primary research, with results made available to the entire world, free of charge. He instituted the Smithsonian Contributions to Knowledge, a series of publications shared with scholarly institutions globally, creating an early international framework for open access. His personal and institutional policy was resolute. Discoveries made under the Smithsonian's auspices or by Henry himself were the property of humanity. He famously refused to patent his own crucial developments in electromagnetism, including the high-intensity magnet and the relay, the very components that formed the bedrock of telegraphy. He believed that to patent such a fundamental principle was to place a toll booth on the road of progress, enriching an individual at the expense of the collective. His influence shaped the ethos of American public science for a century, creating a model for government-funded research agencies like the National Science Foundation and the National Institutes of Health, all predicated on the idea that basic science is a public good, a wellspring from which all other applications flow. Henry's legacy is measured in the institutions he built and the scientific culture he fostered, a contribution of quiet, immense, and foundational significance. Bell's trajectory followed an entirely different orbit, one defined by the immense gravitational pull of commerce and law. His achievement was secured by U.S. Patent 174 Deuce 165, arguably the single most valuable patent ever issued. This document became the cornerstone of the Bell Telephone Company, founded in 1877. Bell, along with his financial backers like Gardner Hubbard, evolved from an inventor into the patriarch of a technological dynasty. His genius extended from the laboratory to the courtroom and the boardroom. The company's early history was a relentless campaign of litigation, successfully defending its patent monopoly against more than 600 challengers, including formidable competitors like Elisha Gray and the Western Union Telegraph Company. This legal fortress allowed the Bell system to flourish, establishing a telecommunications monopoly that would dominate American life for a century. Bell's model was that of the inventor-entrepreneur, a figure who translates a technical breakthrough into a commercial product and builds an industrial structure around it. His work provided the template for the modern technology corporation, where intellectual property is a primary asset and market dominance is the strategic goal. In a fascinating historical irony, the eventual successor to his enterprise, Bell Labs, would for a time become a hybrid institution, a corporate-funded research center that produced foundational, Nobel-winning science, in some ways reconciling the philosophies of both Bell and Henry under one roof. Bell's legacy is audible in every phone call and visible in every strand of fiber optic cable, a testament to the world-shaping power of a protected, commercialized invention. These two legacies, one of public science and the other of proprietary invention, form a single, symbiotic narrative. They represent the essential duality at the heart of technological progress. The modern world is a product of their interplay. The tension between the Henry model of open, foundational research and the Bell model of protected, commercial application is live in every university technology transfer office, in every debate over open source software versus proprietary code, and in every policy discussion about pharmaceutical patents. The digital age, with its collaborative platforms and its fiercely protected ecosystems, is a direct descendant of this dynamic. To understand innovation, we must understand it as a process that requires both the selfless sowing of seeds and the ambitious harvesting of fruit. The myth of the solitary genius, whether in the laboratory or the workshop, dissolves in the light of this history. Progress is a partnership, often unacknowledged, between the discoverer of principles and the architect of applications. The story of the telephone, therefore, becomes the story of Bell Henry, a single, indivisible process where the quiet work of one generation becomes the resonant voice of the next. This dynamic, a constant negotiation between the commons of knowledge and the frontiers of enterprise, continues to define the very rhythm of human advancement.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.